In Lewis theory, we represent valence electrons as dots surrounding the symbol of the element. And so these end up being called Lewis structures or dot structures or Lewis dot structures or electron dot structures. They've got all these different names. The number of valence electrons, as we just learned, can be predicted from the periodic table for the main group elements. And we're only going to be looking at main group elements when we do this Lewis theory. Helium, of course, is an exception because it's in group 8A, but it doesn't have 8 valence electrons. It doesn't even have 8 electrons. So the group number tells us the number of valence electrons. So the electron configuration for oxygen, we just learned how to do stuff like that. What's the electron configuration for oxygen? Well, find it on the periodic table. What's the last term in its electron configuration? It's in the second row, right? 2. It's in the p block. It's going to end with 2p4, right? And then before that is 2s2 and 1s2 before that. Or you can start at the front and go 1s2, 2s2, and then you get into the 2p block and you're 4 into it. So these are the valence electrons, right? How many valence electrons? 6. So then the Lewis structure is O for oxygen. And 6. 1, 2, 3, 4, 5, 6. 6 dots. Yes?
Is there a certain way that has to go?
There's not one right answer, but there are wrong answers. And so what we do is we put 2 on the top, up 1 or 2 on the top, 1 or 2 on the bottom, on the right and the left. And so there's a possibility for 8. And they do end up being similar to the electrons in the orbital diagram. Let's look at that real quick. If we look at the valence electrons in the orbital diagram, two of them are paired, and 2 are paired, and then there's 2 that are not paired. So there's 4 different orbitals here in these 2 subshells. And so top and bottom, right and left is 4. Now, whether you put the 2 pairs on top and right or on the bottom and the left, that doesn't matter at all. So it could be like this. That's fine. But what we don't want is we don't want you to just kind of make a ring around the rosy. 1, 2, 3, 4, 5, 6, or something like that. For one thing, it's hard to count. If they're top and bottom, right and left, you can look at them. It's like looking at dice, and you can see the number without having to count. So this is not good, but the rest of them are. That's a good question. Each dot represents a valence electron. We're going to put them around with a maximum of 2 per side, exact location not mattering, but we're going to put them around singly at first and then pair them. And it's especially important to follow this convention on mastering chemistry. As you know, mastering chemistry can be a real stickler for details. Those noble gases that don't react with much of anything are particularly stable. They have 8 valence electrons. And so when we have 8 dots around an atom, we call that an octet. Just like if you have 8 singers singing together, it's an octet, right? So this is the octet. And so if we see an element like argon, argon has 8 valence electrons. So here's argon. 1, 2, 3, 4, 5, 6, 7, 8. It's full. It's satisfied. Okay? That's what the other elements are trying to do when they react. They're either going to gain or lose electrons so that they can get that octet, or they're going to share electrons with other atoms to get that octet. That's not the real scientific explanation, but it's a little easier to understand. So let's write Lewis structures for the first 10 elements. How many valence electrons does hydrogen have? 1. We'll just give him 1 dot. How about helium? 2. So we'll give him 2 dots. Lithium? Valence electrons? 1. Beryllium? 2. Boron? 3. Carbon? 4. Carbon is in group 4A. We can just look at the group number. How many valence electrons in nitrogen? 5. 1, 2, 3, 4, 5. So now we're starting again and paired up. We already did oxygen. 1, 2, 3, 4, 5, 6. How about fluorine? 7. 1, 2, 3, 4, 5, 6, 7. Again, if you put the single dot in one of the other positions, that's fine, as long as you have 3 pairs and 1 single. And then neon is going to have 8. And so it's going to have 2 on each side. And that's like the perfect. 8 is kind of a magic number in terms of electrons. Now helium and hydrogen, those are the baby brothers, right? They're the little guys. They can't handle 8 electrons. They're happy with 2. And 2 is a duet, and so we talk about a duet rule for hydrogen and helium because they're too small to handle the 8. So here helium has 2 electrons. He's good with that. Hydrogen would like to be like helium and get 2 electrons, so he's going to work on that and try to get 2 electrons. Any questions? According to Lewis theory, we get a chemical bond from the sharing or transfer of these valence electrons, and they're going to do so in a way to get more stable electron configurations. So this is an important distinction between ionic bonds and covalent bonds. Ionic bonds involve transfer. The metal gives an electron to the nonmetal. The nonmetal would be free to take that electron off somewhere else if it wanted to. In a covalent bond, the electrons are being shared. What's the prefix co mean? It means to share, right? A co-op, cooperation, you're working together. Co-sleeping, which happened again last night. Andrew crawled in bed with me. Co-sleeping is 2 people sleeping together, right? Covalent is sharing valence electrons. So covalent bonds are sharing electrons. Ionic bonds are transfer. Question?
Isn't that done to like fill the ring, right? So nothing else can join?
Yeah, we think of it as sharing or transferring in order to obtain an octet, that full 8 electrons in the valence shell.
So if a 7 and a 7 join, nothing else can join, right? 7 valence ring?
Right. We'll get to that. We'll get to that. So the octet rule, it states that in chemical bonding, atoms transfer or share electrons to obtain outer shells with 8 electrons. There are violations of the octet rule, but it's still a very useful rule and it predicts a lot of things. These little guys, hydrogen, lithium, beryllium, they follow the duet rule. They're just trying to get 2 electrons. And really the only atom that we're going to run into of these little guys is hydrogen in terms of bonding. Helium doesn't bond with anything, so we can just kind of ignore him. He's kind of stuck on himself. Let's write Lewis structures for magnesium and sulfur. How many valence electrons does magnesium have? It's got 2. It's in group 2A. So here's magnesium. It's got 2 valence electrons. And how about sulfur? Sulfur has 6. It's in group 6A. 1, 2, 3, 4, 5, 6. So those are Lewis structures for magnesium and for sulfur. It's just valence electrons. So all the elements in a group are going to have very similar electron configuration. So below sulfur is selenium. Selenium. Selenium also has 6 valence electrons. 1, 2, 3, 4, 5, 6. So the Lewis structure is essentially going to be the same.